So where we left off in class, where we're talking about entropy, right? And so the second law talks about how entropy of the universe must always either increase or remain the same. It can never decrease, all right? And so I want you to look right here in your book. So the change in entropy of the universe has to be greater or equal to 0. And so if the change in entropy is 0, if it doesn't change, or the change in entropy is positive number if it does change, right? Because of the second law, it has to be either of those two. It's either 0 if it doesn't change, or it's positive if it does change. So there's two ways that chemists can find the change in entropy. They can do it qualitatively. So you're not going to have a number, but you are going to know the sign in the change of entropy. So you're going to know either it's a plus entropy or negative entropy. And then knowing that sign helps you know what's happening chemically, basically. And in order to get that, what you do is you look at the number of molecules or atoms on each side of your equation along with the phase. Remember, because we talked in class about that, about the rules of the phases. So the side of the reaction that has the most molecules or atoms in the gas phase is going to have the highest entropy. Remember, because in the gas phase, the molecules are the furthest apart, and so therefore they have the opportunity to have the highest entropy. If there's no gases in the reaction, then you're going to go to looking at liquids, and the side with the most molecules in the liquid or aqueous phase is going to have the highest entropy. And then if all substances in the reaction are solids, then the side with the most molecules or atoms will have the highest entropy. Remember, we talked about that in class 2, that more matter equals higher entropy, right? If all things are equal, then you can't determine the sign or change in entropy, okay? And then your book walks you through some examples of this. So right here, it says for each reaction below, determine the sign of the change in entropy, delta S. Okay, so for this one, you have zinc solid plus hydrochloric acid aqueous. Well, you may not know all these. So ZnCl2 aqueous plus H2 gas, hydrogen gas. Okay, so you look at both sides. This side of the equation, the reactants, there's none in the gas phase. If you go over here to the product side, there's one molecule in the gas phase. So this is going to go from low entropy to high entropy. So because entropy increases, your change in entropy is going to be positive. Okay, so that's going to be the sign there. And then B right here, same thing. So I'm going to look at my reactants, my nitrogen, that's a gas right there. And then my hydrogen is a gas. So I'm going to add up how many molecules. So I have 1 nitrogen and 3 hydrogen. So that's going to be 4 molecules on the reactant side. And then I go over to my product side, and it is a gas, but I only have 2 molecules. So this one is going to go from a high entropy to a low entropy state. So my change in entropy, my delta S, is going to be negative. Okay. How can the entropy be lowered, you say? Remember that the second law says it stays the same or increases, but what you have to remember is that the second law says the entropy of the universe will always stay the same or increase, okay? A reaction can proceed even if our change in entropy is negative, but you just know that some specific conditions have to be met in order for that to happen. Okay, and then lastly for C right here, I'm going to look for gases, and I don't see any on either side. So then I'm going to go to liquid or aqueous, and I have none on the reactant side. But when I go to the product side, I do. I have two of NH4OH, right here, and then I have 8 right here. And then this is aqueous, so I even have 1. So I'm going to have 8. I'm going to have 11 molecules on this side. So I'm going to go from a low entropy to a higher entropy state. So my delta S, or change in entropy, is going to be positive. Okay? Here's the units. They're joules per moles Kelvin. So entropy values are a lot smaller in units than the values that we looked at in class for enthalpy of formation, right? Okay, now I want to jump into Gibbs free energy. I know that especially Jonathan said that he was having a little bit of trouble with this. Okay, so we have our equation right here of Gibbs free energy. And in order to know whether or not a reaction is going to happen, what you need to do is figure out the effect that the reaction has on the entropy of its surroundings, right? And a major way a reaction does this is through its enthalpy, right? So remember the enthalpy reaction, delta H, and then it has a little degree equals the sum of the H formation degree of the products minus the sum of the H formation degree of the reactants, right? And remember that the enthalpy has to do with energy change, and a change in energy affects the reaction's disorder or its entropy, right? So if a chemical reaction has a delta H of negative, what's going to happen? Well, it releases energy into the surroundings, right? So the entropy of the surroundings is going to increase. And then greater entropy is going to be an increased delta S, right? Conversely, if our delta H is positive, it's going to absorb the energy from its surroundings. So the entropy is going to be lesser entropy, right? And you're going to have a decreased delta S. So in order to know if a reaction is going to occur, you need to look at the change, the delta H and the delta S under standard conditions, okay? So the value of the change in entropy is going to tell you about the entropy change of the reaction itself. And the change in the enthalpy is going to tell you what's going to be happening to the change in the entropy of the reaction surroundings. Okay, and so that leads us into this Gibbs free energy. So we have Gibbs free energy is what the delta G, the change in the Gibbs free energy, right, is the change in the delta H, which is the change in enthalpy, minus the temperature of the surroundings in Kelvin multiplied by your delta S, or your change in entropy. Okay, so if your delta G right here is less than 0, if it's negative, then the reaction is consistent with the second law and it is spontaneous. Okay, if your delta G is greater than 0, so it's positive, it's a non-spontaneous reaction, and this reaction isn't consistent with the second law, and so it's not going to proceed, okay? So again, if the delta G is less than 0, it's consistent, it's spontaneous, it's going to happen. If the delta G is greater than 0, the reaction is not going to proceed. It's not going to happen because it violates that second law. Okay, so just looking at this then, if my delta G is negative, right, and I have a negative delta H, I have a exothermic reaction, so it's going to have a negative enthalpy. And let's say that my delta S, my entropy, is positive. The reaction will be spontaneous and it will occur, right? Now, delta G will always be positive if it's an endothermic reaction, right? If it's an endothermic reaction, then my delta H is going to be positive and my delta S is going to be negative, and so therefore it's always going to be positive, and these reactions are never going to be spontaneous, okay? So that's another way that you can kind of remember. I know, Jonathan, you said it was a little bit confusing, and I'm kind of explaining what the book says, so it is possible that you're still confused, and if that's the case, please let me know. I don't want anyone to be confused on these two concepts. I don't want you to mix up enthalpy and entropy. I want you to kind of keep them separated in your head. Sorry about my shadows right here. Let me pause it, and I think I promised Lincoln I would work out the last practice problem, so let me do that, and I'll give you some hints for your test. Okay, last I want to work this practice problem for you really quick. And to get my numbers, I'm going to use this chart, and this is the equation I'm going to use. But it says, it gives you a reaction, and then it says they want you to say if it's spontaneous at 298 degrees Kelvin. So what I did is I used this chart right here, and I put in my standard Gibbs free energy of formation values. So for this reactant, it's going to be 125 kilojoules per mole. And then I have my elemental forms, so it's just going to be 0, 0. And then I have my product right. I just want to highlight really quick that remember that the Gibbs free energy or formation at standard conditions of any element in its elemental form is 0, the same as its delta H of formation at standard conditions, okay? So I just want to pop that in here. So then when I'm calculating it out, I use the equation, the sum of the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants, and that's of the formation, right? And so I'm going to do my products. So 6 moles times negative 175 kilojoules per mole. My moles right here will cancel out. Minus 2 moles times 125 kilojoules per mole, cancel out. I'm going to be left with negative 1300, and I just put it in scientific notation. And so, yes, my delta G is negative. So, yes, this is spontaneous, and that's how I know. Hopefully that helps you. Let me go glance at your test and give you a few hints. All right. So for your Module 13 test, on the very back of the test, they are going to give you a chart that has bond energies. You're going to get a table with bond energies. You're going to get a table of standard enthalpies of formation. You're going to get a table with standard absolute entropies. And you're going to get a table with standard Gibbs free energies, okay? So you're going to have tables with numbers and information, and you need to be able to use those in the problem section, all right? So remember in lecture, we went over energy diagrams. Be able to do what we did in class. Be able to tell me if this energy diagram is an exothermic reaction or an endothermic reaction. Be able to tell me which, if you have multiple diagrams, which one has a delta H of a certain number. So be able to get those from looking at energy diagrams. Okay. I don't want to tell you everything, but in your problems, you're going to have to use bond energies and determine the delta H for a combustion reaction. So remember what that means. You're going to have to come up with the equation. Okay. So remember, we do this in class a lot, but you have your reactant, a complete combustion reaction. You're going to add oxygen, and it's going to yield your products. It's going to have water, and it's going to have carbon dioxide. Remember your phases, right? You know the phases when you do that. Remember to balance your equation before you move on. You're also going to need to use Hess's law to determine delta H, be able to calculate delta G. Basically, yeah, just a little bit. I think working through your homework is really going to help. So let me know. I know this video is not the greatest. I just really wanted to get it out for you. Let me know if you have any questions, and good luck.